So you know that electrons orbit the nucleus. Well, based on that experiment you just watched with that YouTube video, that the orbits seem to have special areas. Because what they did is they found those colors that were produced. And those colors are related to energy. The red light, the yellow light, the green light that you observed. So what scientists realized, it was the electrons that could absorb energy from the flame. They would then occupy certain orbits outside of the nucleus, and we could begin to use the light that was released to figure out exactly the position of electrons. That, my friends, is your topic 5. We're going to put these electrons in their proper orbits outside of the nucleus by using the energy that they released in that simple little flame test that you observed. Okay. All right, I'm going to go and erase this now, so I need some more room. If I had you Google the image of an atom, you know what you would find, and you know what you would see. You would see an image that looks like this. You've seen it a million times. There's the center, which is the nucleus, and then we have these electrons orbiting around the nucleus. That's the model that you would see. You're familiar with that. All right, what we're going to do is we are going to look at just a small section of these orbits that exist. So what we're going to do is we're going to take a look at a little small section of them. I don't need to look at the whole complete orbit. I'll get a good picture of what's going on simply by taking a little piece of it and then expanding the view. If you're going to take notes on this, basically today you are simply drawing. You're drawing all day today. So if you want, maybe you go down in your notes, I don't know, probably 6 or 7 lines. And you can put your dot there. And now remember, in that dot, you've got the protons and you've got the neutrons. My camera does not want to focus this morning. Hey, maybe I can do this to make it easier. Let me just put a big circle here. I'll put protons, I'll put neutrons in there. That works. All right, there's the nucleus. We know about that. Now what we're going to do, if you take a look at this, I'm going to go inside here and just grab this very first line. That is an orbit for electrons around the nucleus. And I need to do a lot of color changes, so bear with me. Okay, I'm going to grab this one. When scientists ran that flame test that you just watched in that video, they had to apply a lot of math to the energy that was released to give them a picture of all the orbits that exist out here where electrons can occupy. Based on that flame test that you just saw in that video, they found an area of space where electrons can hang out. Now remember, it does go all the way around. It does a complete orbit around the nucleus. But my friends, the whiteboard is not large enough to do this full circle. That's why I'm only taking a small section of it. But remember, it does go all the way around. But I don't have room. So let me get rid of this. So keep that in mind as I do this. That first area where they found electrons to be hanging out is called a main level. And since it was the first area where they measured the existence of electrons, they called this main level number 1. Let me get this to be a little better. They called it main level number 1. And if you could take main level number 1 and open it up, you would see a smaller area of space where electrons hang out. And that smaller area of space is simply a higher probability for the location of an electron. This more discrete area of space inside a main level is called a sublevel. Once they measured the existence based on the energy that you observed, the colors of light in that video, they had to give it some symbol. And they gave it a symbol of S, just a lowercase s. Well, as you can tell from the video, many colors were released. Many colors in those samples that that teacher was placing in that Bunsen burner. So man, that tells you there's a lot of areas out here where electrons can exist because all the colors were different. They continued to study that light that was produced. And they actually found a second main level where electrons can hang out. And remember, it does go all the way around, but I only need to draw just a sliver of it. That being the second major area where electrons can hang out, they called it a main level number 2. If, and it's a big if, I know you can't, but if you could look at main level number 2, this guy right there, if you could look at it and somehow magically open it up and look inside, you would see that same small sublevel S again for the second time. But at main level number 2, you would see a second sublevel, a larger sublevel than the S. And since it's larger and has more energy than an S, they had to give it a new symbol, and they gave it a symbol of P. Well, as you can tell from that video, there was many shades of color being produced. As a matter of fact, the scientists actually developed tools to measure energy outside of the visual spectrum, which means they could measure microwaves, infrared waves, ultraviolet waves that these electrons would emit. So it wasn't just the visible spectrum, they used everything to begin to map out the position of these electrons. Doing that, they actually found, yep, you're right, they found a third main level. A huge main level. Oops, I need to get this a little bit bigger. Hang on. Get it bigger. There we go. If, and I know it's a big if, just play the if game with me. If we could open up main level number 3 and look inside, bingo, there it is again. For the third time, that little small sublevel S would be in there. For the second time, you would see that sublevel P. Remember, the P is a little bit larger than an S. If it's larger, it has more energy. And so they can measure its existence. But then they hit the jackpot, man. They hit the jackpot. In main level number 3, for the first time, they measured the existence of a third sublevel. And that third sublevel was quite large. The thing was huge. It would hold many more electrons than S and P combined. Different sublevel, larger, different levels of energy. They had to give it a new symbol, and they gave it a symbol of D. Well, with more tests and a lot of math, they actually measured the existence of a fourth main level. Ooh, now this is where it gets nasty. If you take a look at the image or model of the atom, you see how they begin to overlap and get kind of distorted as we move away from the nucleus? This is where the distortion finally showed up, and this was puzzling to scientists for a long time, because that's hard to figure out. So main level number 4 that they measured actually comes over and eclipses part of main level number 3. So main level number 4 comes in here, overlaps main level number 3, just a little bit, and it is the fourth main level, and so you can put this up here, main level number 4. Okay, if my friends, if you could physically grab main level 4, which you can't, but if you could, and if you could open it up and look inside and see what's in there, yes, you're right. You would see that little tiny sublevel S for the 4th time. Yeah, you're right. You would see that P. Ooh, now look at where the P is. The P is way over here. And you're right. You're right. You would see that huge D for the 2nd time. Way over here. And then they hit the jackpot once again. They thought that this D was huge. They thought that was huge. Holy smokes, they found an enormous sublevel. That enormous sublevel, greater than a D, much greater than an S and a P combined, way more energy. And since it was different, they had to give it a new symbol, and the symbol was F. Believe it or not, that's supposed to be a different color. I'm actually using, okay. Hope you can see the colors. All right, sit down and relax, because guess what? Yes, they found a 5th main level. Now, you don't see me drawing this, which means you don't have to draw it. But I'm going to tell you that they did find a 5th main level. It's almost impossible to draw on a 2-dimensional board, because remember, electrons have a 3-dimensional space to travel, and so it gets to a point where I really can't draw some of these main levels. But I'm going to tell you right now, there is a 5th main level. Stop. Look. My friends, it's a pattern. Some of you are really good at patterns. Look at the pattern when it comes to the main level and the number of sublevels that are inside. They match. Oh, I see it now. Look. Main level number 1, just 1 sublevel. Main level number 2, 2 sublevels. Main level number 3, 3 sublevels. Main level number 4, 4 sublevels. I know, I'm way at the bottom of the screen. There's 4 sublevels. So take a guess how many sublevels are in main level number 5. Yeah, there's 5. And guess what? You probably already know the first 4, because the pattern repeats itself. You already know that main level number 5 has to have an S, a P, a D, and an F. But you've also noticed that every time we have progressed farther from the nucleus, another new sublevel shows up. And yes, another new sublevel did show up in number 5, larger than these, and they had to give it a new symbol, and they gave it a symbol G. I'm glad you're sitting down because they found a 6th main level. Now you notice I'm not drawing this thing because this whiteboard is not large enough, and it's impossible to draw the overlaps. But here's what you probably already know. You probably already know that in the 6th main level, you have 6 sublevels, and you already know the first 5. Because in main level number 6, it has what main level 5 has. It has these 5, S, P, D, F, and G. And you've noticed every time we progress farther from the nucleus, a new sublevel shows up. And sure enough, in number 6, that sublevel showed up. That's supposed to be an H. I think I have a glare on my screen. Maybe that's better. Yeah, that helps. Yeah, well, just relax. They found a 7th main level. Hey, this took them years to figure out. It took Einstein, Heisenberg, Planck, de Broglie, some very, very intelligent people, way beyond the normal human spectrum, to figure this out, make a model that matches their observations. Dude, that's not easy. It took a long time. Okay, I'll save you the boring details. Yes, they found 7 sublevels inside main level number 7. Okay, now look, there's another pattern going on here. But it's kind of weird. Just look at these. Look, look, look. Come on, look. Wait a minute. There's a pattern, but something's not right. You see it? All right, here's the pattern that you should see. There's always an SPDF, and then the next newest sublevel was a G, and then the next was an H, then the next was an I. All of a sudden, they went in alphabetical order. But originally, they were selecting letters throughout the whole alphabet in no particular order. I mean, SPDF, what the heck is that? GHI? Ooh, sounds familiar. Okay, so there's a clue there, and the clue is this. Sublevels G, H, and I do exist. They are there. Humans have placed electrons out there to measure their existence and all that stuff. But an atom on its own, without human influence, does not use G, H, or I. So even good old 118, the largest one on this table, element 118 on its own does not use G, H, or I until humans come around and start forcing electrons out there. We don't want to look at human influence. We want to look at just their natural ground state for atoms. Just what did they do on their own? Which is good news for you, because guess what? You don't have to worry about G, H, or I. Now, they're out there, they exist, but I don't want to worry about human influence. I just want to know what the atoms are doing on their own. Okay, take a picture of that. A mental picture. Put your phone away. A mental picture. So burning those salts, producing those different shades of color, and obviously some pretty sophisticated materials beyond that, they found 7 main levels for electrons to hang out. Within these huge main levels, there seems to be smaller areas where electrons can be located, called sublevels. Now, I've been telling you throughout this whole topic 5 that there's a difference between S, P, D, and F. And I kept on telling you it's the size. We need to dissect and take care of the size difference between S, P, D, and F. So here's what I am going to do. I'm going to get rid of this. And right here, let's make a table that helps distinguish an S from a P and from a D. Probably going to be the most important table of your life. I'm going to start it right here. Let's go sub-level. This table is going to have 3 columns. But let's just take a look at column number 1. Sublevels, you guys, you only have 4. S, P, D, and an F. There they are. I kept on saying as I was drawing this, oh hey, this sublevel is larger than the other sublevel. Okay, how do you measure the size of a sublevel? Well, they measure the size of a sublevel in terms of orbitals. Number of orbitals. Now you're thinking, what the heck is an orbital? Just think of an orbital as a smaller area of space where you're probably going to find those electrons. Very small area of space where you're going to find electrons. And there seem to be a different number of these tiny little areas inside these different sublevels. Through a lot of math and some calculations and experimentation, they found that an S sublevel seemed to have just one of these orbitals or discrete areas of space. The P, they found and measured 3 little orbital areas. D, 5, F, 7. Final column to your most important table of your life. They found that these orbitals, these very, very tiny areas of space where electrons can hang out, there seemed to be a limit to how many electrons could fit inside those orbitals. That's your column 3, number of electrons. They found through all of their tests and experiments and applying a lot of math that you could only place 2 electrons per orbital. 2 electrons per orbital. Which means if there's only 1 orbital, when I times that by 2, an S can only hold 2 electrons, and that's it. That sucker is closed and full. A P, now having 3 orbitals, and if you can put 2 electrons per orbital, then a P sublevel can hold up to and no more than 6 electrons. And then the pattern continues. A D has 5 orbitals, well, 2 electrons per orbital. A D sublevel can only hold 10 electrons and no more. You cannot put 11 electrons in a D. It doesn't fit. In the F, 14. Okay, I'm going to pause here for questions. Our job now is to take any atom, find its number of electrons, and simply organize those electrons in their proper positions. That's it. So let's start off small. let's start off really small so you get the idea behind this. Let's start off with good old nitrogen. Okay, here comes topic 3 back in your face. How many electrons does nitrogen have? You have to go back to topic 3. Because if you don't know, you're going to get all these wrong. If you go back to topic 3 and remember the A and the Z number, well, the A number is the mass, which is the protons and the neutrons. Has nothing to do with electrons. Ah, yeah. There's the Z number, and the Z number does inform you about the protons and the electrons. There's the number of electrons inside a nitrogen nucleus. That's what I want. So, what I do is I simply do this. Hey, I've got nitrogen. His Z number is 7, which tells me I have 7 electrons to place. I am going to show you how to take those 7 and put them in their proper positions and kind of write out the address for these electrons. Okay, watch this. Here comes his 7 electrons. Cha-ching. There they are. Yes, they're M&Ms because I got a whole bunch of M&Ms on my board from our lovely percent example. Let's begin to place those 7 electrons in their proper positions around the nucleus for nitrogen. I would highly recommend you do not write this. You just simply need to sit back and watch and listen. Watch and listen. Okay. I am going to give electron number 1 a little push. The protons in here are going to begin to pull that electron towards the center of the nucleus. It's not going to collide. They're going to get close. Okay, this electron, his goal is to get as close as it can to the nucleus. So what it wants to do, it wants to find the nearest open main level. Well, since this is electron number 1, the nearest open main level is number 1. And once that electron gets inside main level number 1, it wants to find the nearest open sublevel, which in this case is S because it's the first electron. And once he gets in there, boom, he then begins to orbit around the nucleus. So let's put him there. Now, watch how I write this. This is what's tricky. That first electron is in main level number 1. He seems to be inside sublevel S. This is where you have to pay close attention. Watch this. How many electrons are in there now? Well, just 1. That's the address for that electron. That's where it lives. Okay, let's continue. Let's give electron number 2 a good old shove. It wants to get as close as it can to the nucleus, so it's looking for the nearest open main level. Well, what's open? Well, this is still open because an S holds up to 2 electrons, and right now there's only 1 in there. So this guy's going to go cruise in. It's going to get inside main level number 1. The nearest open sublevel will be an S, and once he gets in there, boom, he joins the other one, and the 2 begin to orbit around the nucleus. So at this point in time, what do I have? I have 2 electrons. There they are. In the S, occupying the main level number 1 space. Bingo. Hey, you've got 5 more. You've only placed 2 of 7. You've got 5 more to go. All right? Oh, but look, my friends, look. The S, you already have 2 in there. Guess what? That's all it can hold. This S sublevel is closed. It's full. You cannot put a third one in there. So actually, the whole main level number 1 is closed. But you still got 5 more to go. So let's give this third electron a good old push. It wants to get as close as it can to the nucleus. The nearest open main level now is only main level number 2. The nearest open sublevel is just the S. And once he gets in there, boom, he begins to orbit the nucleus. Okay? Hey, where is that guy? He's in, watch this, he's in main level number 2. He's in that sublevel S. And as of right now, there's only 1 in there. You've got more to go. So you give this guy a push. Electron number 4, you give him a push. He's going to go in. Well, that main level number 1 is closed. It's full. The nearest open main level now is still main level number 2. The nearest open sublevel is still in S because it can hold 2. He gets in there, joins this one, and the 2 begin to orbit. So, at this point in time, I've got 4 electrons, and here they are, in their proper positions around the nucleus. 2 in this S, 2 in this S. I've got 2 in this main level, and so far I've got 2 in this main level. You've got 3 more to go. All right, well, electron number 5, give him a push. Ooh, no, 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 no. Main level number 1's closed. And hey, look. This S, it has 2 electrons. Looks like that baby's shut down as well. Full. The only option, yeah, it's still main level number 2, but now it's sublevel P. Where is that 5th electron? Well, it's main level number 2, all right, but now it's in sublevel P. And at this point, there's only 1 in there. Next electron. Well, 1 in, yeah, those are all shut and closed. You give him a shove, he goes in. The nearest open main level is still number 2. The nearest open sublevel is P. And when he gets in there, now you've got a total of 2 in there. Well, you've got 1 more to go because 2 and 2 and 2 make 6. You got 7. Give him in there. Give him a shove. Nearest open main level, 2. Nearest open sublevel, P. Get him in there. Total. Bingo. Oh no, here comes my cat. What is this? This is called Electron configuration. Whew, look at that. Electron configuration is what that is called. Hang on, where's yeah, forget it. This is the goal for chapter 5. This is goal number 1 for chapter 5. You see this right here? That's what we want. Now, to a trained eye like mine, this tells me a lot about this atom. I don't even care what it is. If I see this electron configuration, here's what I can tell you about this atom. I can tell you that this atom is a non-metal. This atom does not conduct electricity. This atom is not malleable. This atom does nothing when it comes in contact with acid. This atom would love to gain electrons from a different atom, combine with that atom and form a type of salt. That's what this tells me. And that's what it's going to tell you eventually. This tells me everything I need to know. Why? It's the electrons. Electrons tell me the behavior of an atom. Okay. I'm gonna do this. Okay, cat, knock it off. All right, let me show you just one more, and then I think we better stop this for today because this is a lot to take in. in one period. Let me move these out of the way. Let me reset everything. Let me reset everything. Okay, let's pick a larger one now. I'll go faster, a little faster, but again, you can see the pattern and how these things fill. Let's go with you already know how many electrons and protons for magnesium. If you don't know, your topic 3 is going to create a huge headache for you. You should already know from topic 3. It's that one right there. All right, so your topic 3 tells you you have 12 electrons to place. Two, 4, 6, 8, 10. There they are. There's your 12. Okay, watch this, my friends. We just reset the bar, and then we start again. I'm going to give, can we take 2 at a time? Okay, I'll go 1 at a time. Okay, electron number 1, nearest open main level. Number 1, nearest open sublevel is S. Once he gets in there, I'm like that. Electron number 2, he comes in. Nearest open main level is still 1. Nearest open sublevel is still S. Once he gets in there and joins that one, you have a total of 2 in there. Now, that's significant because 2 is the maximum for an S. This thing is closed. Now I'm going to go in pairs. Let's give these 2 electrons a little push. The nearest open main level is number 2. The nearest open sublevel is this S right here. Those 2 guys get in there. Where am I right now? That's significant because that 2 tells me this S is full. This thing is done. You can't go there. Hey, let me give these 2 a shove. Give these 2 a shove. The nearest open main level is still main level number 2. The sublevel is P. When those guys get there, that's what I have as of now. 2, 4, 6. 2, 4, 6. But wait a minute. There's still more room. There's more room. Because a P can hold up to 6. You're only at 2. Here, let me take out these browns and let me put these greens in there. That's the reason why I had those greens. Sorry, just relax. It's still the same thing. So now this, I have more room. I have more room because they can hold up to 6. I think my 6 is almost gone. So I'm going to give these 2 a shove. Closed, closed. These 2, nearest open main level is still number 2. Nearest open sublevel is still a P. Those 2 guys get in there. Where am I at right now? A total of 4. You still have 4 more to go, my friends. Alright, well you give these 2 guys a shove. Nearest open main level is a 2. Oops, that S is closed. Those 2 guys get inside here. Join the previous 4 for a grand total of 6. You still have 2 left, but look, that is significant because 6 is the max a P can hold. Closed, closed, closed. Ooh, look where these 2. These 2, the nearest open main level now is 3, and in main level number 3, the first sublevel is this S. And these 2 guys go inside here. They get inside that S sublevel. Where are those 2 electrons? Main level number 3. Sublevel S. How many are in there? Bada boom, bada bing. When I see something like this, I can tell you that sucker is a metal. It's shiny. It's malleable. It will react with acid. It will conduct electricity. It will lose electrons when combined with something else. What is that something else? Probably going to be a non-metal to the right side of the table. It will form a salt. I just dropped the mic. Dude, that is huge for us. That's huge. Okay. Like I said, that's a lot to swallow in one day. Don't worry. We got weeks of this. So here's what I would recommend you do. Take topic 5 and put it on the back burner. You better get inside my Canvas and finish topics 1 through 4. They all should be submitted by now. If you have not submitted all 4, you are digging a deep, wide hole. Because look what's coming in your face now. And it's going to get worse. We're going to expand on this, and we got many more things to look at in topic 5. It just keeps going and going and going. You got to catch up to me, man, or you're going to build a hole, dig a deep hole I can't get you out of. So, I would put